Hi, my name is Jennifer, and this is Jasmine. We're both principal investigators for the San Marino High School team, and our experiment is on Fibroblast Division in microgravity. So for some background, cell division is an integral component of life. Cell division occurs in all organisms. So our purpose was to discover the effect of microgravity on cell division and to compare the rates of cell division in the absence of gravity. Our hypothesis was that if cells are exposed to microgravity during their life cycles, then there will be a reduction in cell division because of a disorganization of microtubules, which you can see in that picture, because microtubules help cells to separate because it allows the chromosomes to connect to the microtubules so that they are separated into different cells, as well as the change in actin filaments, which allows the cell to form a cleavage furrow. The chromatin becomes less dense, so the chromosomes have difficulty forming, and increased apoptosis, which is cell death. So some of our materials are a type 3 FME, mouse embryonic fibroblasts, Eagle's minimum essential medium, and fetal bovine serum, which both contain nutrients and amino acids needed for cell growth. Formaldehyde, which is our inhibitor, which stops the growth of cells. A light microscope to observe the cells, a hemocytometer to count the cells, and trypan blue to stain the cells so we can determine which are alive and dead.
Okay, so assembly procedures. We choose to use a type 3 FME, which has 3 compartments. In the main volume, we filled it with the Eagle's minimum essential medium and the fetal bovine serum, and that's the growth medium for the cells. And in short ampule A, that's where we place the fibroblast cells. And in short ampule B, we place the formaldehyde, which is the fixative. So to initiate our experiment, we crack ampule A to release the cells into contact with the medium so they will start growth. And to terminate the experiment, we crack ampule B to release the fixative into the solution so the cells will stop growing. And our experiment lasts 9 days. Our experiment hasn't flown yet. It's going to fly in the fall. So we did some ground truth experiments first to test the growth of the cells in different temperatures because there's no incubator aboard the ISS, so we want to see how the cells would grow in room temperature. So as you can see, incubator growth is much better than in room temperature, but we found out that if we start with 750 cells instead of 500, then the growth in room temperature would be much better. So our conclusion, so growth was more favorable in the incubator, and we think it's because the incubator mimics the internal temperature of animals, and that's where the cells come from. And the cell growth is greater when the initial cell count is increased from 500 to 750. And more conclusions will be drawn after our flight actually flies into space. So we want to thank the following people and organizations. Mr. Wyatt Colo for being our advisor, Dr. Susan Kane and Ms. Erin Denny from City of Hope Cancer Center for providing guidance, materials, and lab space. Also CASES, San Marino Unified School District PTSA, and the Stephen and Mary Birch Foundation for their generous donations. And the Smithsonian Air and Space Museum for hosting this event, and NanoRacks and SSEP for making this possible. Thank you.
And a good teachable moment at this point is that the ground truth assessment that you're doing now can really maximize the science return for the flight experiment because you have the ability to reduce concentrations of all fluids and solids up through launch. So you should be, all of those folks in the room, the flight teams that are preparing to launch in the fall, doing that kind of analysis now can maximize the concentrations that you should use for your flight experiment. All right, well, let's thank the team from San Marino, California.